Welcome back to High Tech Heroes. Joe Cychosz is here, and he's been showing us parts of old computers. What computer parts are you going to show us next, Joe?
Well, the next machine Seymour Cray designed was the 7600, and I have a photo here of the machine at the University of Manchester. And it's about 11 feet square there, and a little room inside the center there for the CEs to keep their scopes and have a little office and stuff.
Now, I guess you've been, with a couple of exceptions, you've been following the Seymour Cray machines through history.
Pretty much so. Those are the ones that I know best.
Now, I guess he sort of set the performance curves for the most highest performance computers you can buy off the shelf since sometime in the late 50s.
Right. This might be what you consider the first supercomputer. It definitely was the computer that was used to measure supercomputer performance after that. A Class 6 supercomputer was so many 7600s.
I see. And this is, I've heard a lot of stories about this machine. You can see it's open. It has a square, and in the middle, I guess, is what they used to call the CE's office, right?
Right, exactly.
So that the person who had to fix the machine could just go inside. It's big enough to be like a cubicle today.
Yeah, one of the major architectural changes in this machine was the addition of segmentation into the functional units. So not only could you do many operations in parallel, but, for example, if you wanted to do a series of adds, you could have multiple adds going on in progress. You'd start the first add, it would be partly through the addition, and an additional add could then start in behind it. It would cycle through that.
So more parallelism.
Right.
And isn't there a story about this machine, how they, I guess Control Data decided to build the STAR-100 instead of the 8600, and then after they had written a lot of programs at Livermore for the STAR, they had some loop code or something?
Yeah, you're thinking of Stack Lib, written by Steve McGrogan. Basically, they took many of the vector operations. These are operations that are performed on arrays, Fortran arrays, and wrote subroutines. And that was done for the STAR-100. Packages that then ported over to the 7600 and optimized. And I guess
76. So essentially, they had a library of things which would perform loops, which did the same thing as a star vector instructions.
Right. For example, add two arrays together or multiply an array by a number.
And that then worked faster on the 7600 than it did on the
I believe so.
STAR-100. That's pretty amazing.
At least I think Livermore came to that conclusion.
Yeah.
Anyway, I brought a module. This is similar to the again the 6000 designed for heat conduction, as well as reducing the distance between circuits and getting the circuits actually closer together. There are 8 boards in this machine, much like this one here that I'll lay in front.
So there's 8 boards stacked up
inside a module. I've taken one apart and taken off the black cover.
So this is a board just that you pulled out.
Right.
It's got pins along the edge, tiny transistors.
Yeah, to give you an idea what the transistor speeds were at the time, this is a 1 nanosecond switching transistor. The 6600 started with 5 nanosecond
So switching time of 1 nanosecond. That's
so,
still...
technology was just moving along.
Okay, and heat conduction out of this thick aluminum bar.
Right, and also the addition of a cold plate in between each of the modules, where this was just open air in the 6600 module.
Okay, and what do we have next? Oh, look at that.
Next is the big mystery machine here. And this is the A600. This is the last machine Seymour Cray worked on for Control Data. And it was sort of his transition machine between the 7600 and the Cray 1, which he started in 72 when he left Control Data.
That's a beautiful machine. It looks like a flying saucer. And it is. It's shaped sort of like the Cray. It's shaped sort of more like the Cray 2 than the Cray 1.
Yeah, it's a circular machine. The CPU's in the center there.
And the power supplies are all along the bottom.
And to give you an idea, that's the same girl that was in the previous show you had when Seymour showed his Cray 2 3 machine.
But at a different company, I think.
Yes, a different company.
And well, this is a famous machine, but it still was core memory. And
it was also the machine that he transitioned into 64-bit memory, went from 60 to 64. Still one's complement.
Still one's complement. And did this machine ever work?
Yes, it did.
Well, that's remarkable. It's too bad it was never out. So, what do we have next?
Next, we have the Cray 1, and I brought a slide from the machine. I believe that's at Livermore.
Okay, and so you have a slide of what, Livermore's machine room with the Cray 1 in it?
That's a circular-shaped machine. There are 12 columns there.
Mm-hmm. So it's actually shaped like a C from the top, right?
Right. And there's little benches to sit on for the CEs that work on it. That's where the power supplies are stored.
Okay.
And this is a two's complement machine. You convert a two's complement. He's also pretty much at the limit for serial computing, and so he went with vector processing.
This is still a fast machine and still in use, right?
Yes. I've brought a module from the machine. Cray Research was kind enough to loan us some modules, and here is a module from it. It's quite heavy. There's a large copper plate in there for conducting heat. There's two boards. There's actually another board just like this on the other side.
Yeah, it is pretty heavy.
And I guess one of the interesting design things, there are 9 unique chips in the whole machine.
So there's only 9 different chip types.
9 different chips, yes.
And mostly, I understand this is made out of ECL, and there are 5 NORs, I guess.
Right. And use 1K bipolar RAM for the memory.
Yeah,
There's room for about 100. Well, there's room for 144.
So this still is heat conduction. You conduct the heat out of this incredibly heavy piece of copper.
Right.
And
to get good heat conduction, they had wedges that came in against the boards that they screwed down, and the cold bar.
Right.
Then, and I have an open view of the machine here.
Mm-hmm.
Clip.
Okay.
There you go. And that shows you the power supplies with the Naugahyde seats off and the skins off.
Right.
And one of the big innovations in this machine was the cooling. They used casted stainless steel tubing for the cold bar. And that was they were the first ones to do that. And the reason why is they needed better heat transfer.
They cast the stainless steel right into the aluminum cold bars.
Exactly. They use stainless steel because copper melts in the casting process.
Right.
But in 7600, it was pinched tubing, and there was a heat loss between the copper and the aluminum, so they had to go with a tighter boundary using casting. It was about 4 times the heat transfer.
Uh-huh. Okay. And what do we have next?
Well, the next machine is the Cray 2, and I've brought a slide of that. And this sort of shows the Cray 2 is a circular machine, 4 CPUs. It has 4 CPUs.
See, it still is shaped like a C.
Yes, still shaped like a C. In the background there, you can see a cooling tower, and it was a liquid-cooled machine. The boards are immersed into a inert fluorocarbon and circulated. And this gave them very uniform cooling across the circuits and across the
So
modules.
These circuits are all underwater, so to speak. I mean, they're in fluorinert or some sort of cooling fluid.
Well, it's both chemically inert and electrically inert, so it's non-conducting.
So
it's much like
matter
oil and
that
transformers.
It's underwater, huh?
Right.
And that conducts away the heat much faster?
Yes. They needed, again, 4 times improvement in heat conduction in this machine. I brought a module with, show you, I'll set it on its side here.
Okay.
And there are 8 boards in here, bolted together.
Right.
And then on the side here, you can see they're separated, and that's where the liquid is forced through.
So it's forced through here, but they actually stand they stand horizontally like this.
Correct.
In the machine, and it's all in intimate contact. It looks like there's no space between the chips and the boards.
And you can see there's no pieces of copper or aluminum to conduct the heat. It's all done by the liquid that's being pumped through there.
Right. And the edge there's an edge connector here that's covered, or it's an end connector.
Right. And that plugs into
Now,
the center.
when they wanted to test this machine, how would you test it if it's all underwater?
Well, they had 2 ways. One, they would just sense from the outside using, there's a little beads in there that they could sense the electrical signals in the wires, even though they're all inside the tank.
Okay, so they had little transformer primaries, and you put something on the outside and just couple through the glass.
The other way is without the liquid in it, they would pulse it. and they send a short burst through it, not long enough for it to heat up and do any
like
damage
a
to the
millisecond
machine.
or something, and then they would run a program. Well, I mean, what can you in a millisecond? What can you run? An instruction or two? Or?
Well, fire up a instruction or maybe 2 instructions.
No, I think in a millisecond you could probably run thousands of instructions, right? I mean,
well, but I'm not sure how they
tens of
debug it. I
thousands
think
of
they just kind of
instructions.
pulse it through the circuitry to make sure the circuit was working.
Anyway, okay.
The other thing they used was thermal scans to look at both the Cray 1 and the Cray 2 machine to see cold and hot spots in the machine. I have a slide kind of showing the liquid flowing over the boards and kind of bubbling a little bit.
Oh yeah. There it is. Yeah. Mm-hmm.
And this is a large memory machine. This machine had 256 million words of memory shared between 4 CPUs.
Oh, I can't really tell what I'm looking at. That's the top of the machine?
That's the top of the machine. So
And there are bubbles then under the glass on the top?
Well, you see the liquid on the top of the glass, and that's sort of looks like bubbles.
Are those the circuit boards? I thought they were horizontal. Those are vertical?
Those are the tops. I'm not sure what those circuits are.
Okay. Okay, well, thanks a lot for coming to show us all this stuff, Joe. I'd like to have more time. We could just about take time to go through each one of these machines and make a show of each one. It's really, really interesting stuff. So, come back again and have a pleasant flight back to Purdue.
Yep, thank you.
Tune in again next week for High Tech Heroes.
Thank you for joining us this week for High Tech Heroes. Be sure to tune in again next week when we will bring you more entertaining information about the people and ideas behind the scenes in high-tech industry. And now, this is your announcer, Bill Weigel, wishing you the best of luck and a pleasant week. Au revoir.
This episode of High Tech Heroes has been made possible in part by grants from Ling Systems Incorporated of Lafayette, Indiana, Supersoft Incorporated of Sunnyvale, California, Kinetic Microscience of San Jose, California, and Cybernetic Arts of Sunnyvale, California.